Okay, perfect. Let me have 1 minute. Yeah.
Do I draw my pictures?
No, it's okay. I'm ready.
All right.
We can start.
Pedro, part 2.
Okay, very good. So last time we did mostly kinematics, and the idea today is to start studying some dynamics, mostly based on examples. So the idea of the bootstrap is, of course, orthogonal to the idea of examples, is the idea of trying to find the general space of theories and so on. But it's very useful, of course, to have a look at examples to understand a little bit what kind of animals do we expect to encounter, what kind of analytic properties should SS matrices have, and so on. So let me remind you just of two of the things that we saw last time. One was that we have these particles, for example, two particles colliding one against each other, like P1 and P2. As we said, we are in 2 dimensions, so you see P1 is moving to the right, P2 to the left. They will meet eventually in the second blackboard up there, right? So they will meet and scatter. One comes with some rapidity θ1, the other with some rapidity θ2. If you construct the center of mass energy, P1 plus P2 square, you get something like this that depends on the difference of rapidities, which is, of course, what makes sense, because boosts just shift these rapidities, so that's what's Lorentz invariant. And when the masses are equal, this becomes this expression here. Okay? If you remember, we also said that under crossing, S goes to T, which is equivalent to theta going to I pi minus theta, right? Which is almost begging for a geometrical picture. And indeed, the picture that we usually draw for this scattering process is that I have 2 particles, you see? And this would be particle 1, this would be particle 2. And if we say that associated to the center of mass there is some angle theta, then nicely here indeed it looks like it's the complement, so here it would be I pi minus theta, right? So that's how we see that this angle here would be the crossing of that one over there. So indeed doing theta to I pi minus theta amounts to crossing symmetry, looking from the process from this direction instead of this direction, right? And then, what were we saying? We were saying that physics, we have physical 2-particle processes. For example, in such collision, if I assume that this has mass m1, this has mass m2, this has mass m1, this has mass m2. Remember that when you have m1 and m2, we said there were 2 possible processes, what we call the easy and the hard one, or the transmission and reflection. So here I'm drawing the easy one, the one where the kinematics are such that the momenta are just conserved. So m1 goes to m1, m2 goes to m2. That's why they are rigid lines with the same slope in the past and in the future. And then physical 2-point processes would happen for S bigger, in this case, to m1 plus m2 square, or T, which is 4 minus S, bigger than this value. Okay? So one thing I wanted to write to you is an example of an S matrix where we see this. We see that there's something going on for this value of S, there's something going on for the corresponding value of T, and that's why what we are going to start now is to write down an explicit expression for the S matrix where we will see these two particle processes and these cuts, and we'll be able to make a few comments about it. The other thing we saw was related to multi-particle scattering, and there we considered the scattering where we fixed n minus 2 of the momenta, the white lines here, and then we saw what the red one, the orange one, I don't know if you can tell that these lines are orange. These two lines, we fix them by momentum conservation, right? If we impose all the other ones. And what did we impose for these guys? And here I'm using light cone coordinates. That particle 1 is at rest, so P1 is 1, 1. And then P3, this line 3, goes to the right with velocity x, so very fast, x is very large. x4 is x squared, x cubed, and so on, all the way up to xn minus 3. So it's what I was calling multi-regi, and Tom pointed out it's also called proliferation. Is it true? Proliferation?
No, sorry, that's something else.
No? Okay, so it's a game called multi-regi like last time. And
Strong ordering and momentum.
strong ordering, where there is this strong ordering where we have fast particles faster and faster and faster. Now, what happens by momentum conservation? By momentum conservation, you conclude that this indeed would be what happens, this process, if I scatter a very fast particle, and then this particle 2 will be almost at rest. Okay? So this particle 2 is almost equal to particle 1. This particle n is almost equal to particle n minus 1. Okay. We are going to use this later, but this was just a summary of one of the things we saw last time. So any question about this two blackboards? No? Okay. So let's write. So here is an example of an S matrix. So I will write it and tell you which theory it corresponds to, but let me first write it down. So here is the S matrix, or let me tell you right away what it is. This is the S matrix for what is called the lightest breathers of Sine-Gordon. So there is a theory in 2 dimensions called Sine-Gordon theory. We will discuss more of it in a few minutes, but it's basically d phi, a kinetic term, and the potential is a cosine of phi. That's why it's called Sine-Gordon. The equations of motion have a sine, right? So its potential is cosine of phi, periodic potential. In that theory, if you consider small fluctuations of your scalar field, the smallest ones are called the breathers, just small wiggles of your scalar. It's what you would call the fundamental scalar excitation. When they scatter with each other, they have an S matrix. In this theory, this S matrix has a single bound state. So in this theory, in this channel, there exists a single bound state in this channel. And again, we'll say a little bit more about this soon. But let me then write to you what is this S matrix. It's a very simple S matrix. And here it is. Square root of S minus 4m squared. Downstairs I'm going to write the same thing. Square root of S minus 4m squared. And now I'm going to subtract downstairs the same thing with S replaced by m bound state square. M bound state square minus 4m squared. Exactly the same thing inside the square root with S replaced by mb squared. And here, instead of a minus upstairs, I put a plus. Plus square root of mass of bound state square, mass of bound state square minus 4m squared. Okay. So it turns out that there is a single bound state in this channel. This bound state has mass mb. Okay? Yes?
Is there a distinction between these two little S's you're drawing?
No. This one, of course, yes, right? But this is a serious S. These ones are the same. Yeah. Okay. Okay, so in the notes, there are like 1, 2, 3, 4, 5, 6, maybe 10 small questions about this S matrix, so that you are encouraged to think about, but let me make a few comments that will answer some of them already here. So let's look at this S matrix. Let's suppose someone gave this S matrix to us, and let's learn a few things about this theory that we see from this S matrix. So first we see a couple of things. So we see that what are the analytic properties of this S matrix? Let's write it in a complex plane. What do we see? So we see that there is a square root of s minus 4. So there is a cut when s at s equal to 4 and a cut at s equal to 0. Right? So let's draw it. So there is 4 here, 4m square, and there is a cut, and there is 0, and there is another cut. Right? What else do we see? We see that there is a pole, because as I said, I have square root minus the same thing with s replaced by mb squared. So of course there is a pole at mb squared. What else do we see? I'm forgetting one obvious thing from this picture. So I wrote one pole, two cuts. What else am I missing from the analytic properties of that simple function? Crossing, good. So that function, that's a good comment. So there was this comment that function, there is a nice property, you see, s appears multiplied by s minus 4. That means that the S matrix of s is equal to the S matrix of 4m squared minus s, which I remind you is t, right? And so this is crossing symmetry, is the fact that the S matrix is invariant under swapping s and t. So that's a good comment indeed. Right? So this is crossing symmetry. Okay? It can help you understand what is missing from the analytic property picture that I'm drawing here. Right? So what am I missing? Another pole. So let me draw the other pole. Let me put a small ball for the other pole. And indeed, this pole is at what position? It's at 4m squared minus m mass of the bound state square. Right? So what's the physical meaning of all these singularities? Well, s bigger than the square of 2m was the two particle cuts that we said. So this is when we have two particles or more flowing. Right? This smaller than 0 means t bigger than 4m squared. Right? S smaller than 0 is t bigger than 4m squared. So these are two particles or more in the cross channel. Right? So this would be two particles or more in this cross channel. And similarly, this m of the bound state, right, this guy, this residue, would correspond to a bound state, to a pole, where here I have 1 over s minus m of the bound state square, right? Times what? Times the coupling for producing this bound state and annihilating this bound state. So the residue is g squared, where this g is what we call the coupling. It measures the strength by which these external particles couple to the bound state. Right? So we could, maybe to be more rigorous, we could write g with index m bound state to indicate it's like a cubic coupling between a particle of mass m, two particles of mass m, and one of mass m bound state. And what about this? What is this pole here? This is the exchange. Instead of being creating the bound state that propagates, it's like you exchange this bound state in the T channel. So this would correspond to this exchange, right? And how, when we look at poles of the S matrix, how do I know if it's an S channel or a T channel? Right? What's the difference between these two poles as a function of S? How can I tell which one is which? Well, this pole is what? Is g squared divided by t minus m of the bound state square, right? And t is 4 minus s, so this guy has negative residue. And this guy has positive residue. So the S matrix has a bunch of poles. The ones with positive residues are your bound states, and the ones with negative residues are the cross channel. Okay, they are the T channel exchange. So this is coupling, and here we have G square positive. This positivity of G square is basically the reflection positivity that I think we'll see in the next lecture, applied to proving the unitarity bound, for example. Okay. Okay. Good. So that's two properties of this S matrix that we have. What about the probability? Remember that we said that the probability of two particles going into two particles at some energy S, where S needs to be bigger than 4m squared to be in a physical process, right? In other words, when we do physics, we are here. So this is, in this line, is where our lab is, right? This is where we do physics. We are right above 4m squared. And then what was this probability? If you remember, this probability was the absolute value of the S matrix square, right? So what is this? So let's look up there. Notice, let's see, what do we learn about this S matrix concerning this? This quantity here, what can you say about whether it's real, imaginary, purely real, or a little bit of both? What would you say about this square root here? Right? So you see that the bound state, if you have a bound state, right, the mass of the bound state is between 0 and 2m, right? It's a pole, it's a bound state. It's between 0, as we see in the picture, right? It's between 0 and 4, right? And therefore, this term is positive, this one is smaller than this, so this is purely imaginary. So this square root is purely imaginary. And what happens to the first square root when s is bigger than 4m squared? It's purely real. So we have purely real plus I over purely real minus I. What's the absolute value of this? Right. A plus I over A minus Y. What's the absolute value? 1. Right? So this is equal to 1. Okay. So in particular, what is the probability of starting with two particles and producing n bigger than two particles? Zero, right? Because we already saturated everything with two particles, right? And these kind of theories are what are called the integrable theories. Okay? These are theories that have no particle production. Okay? This comes about, having no particle production comes about when you have extra conserved charges that don't allow for two particles to go into more particles by virtue of this conservation loss. Okay? And clearly this seems to be an integrable theory. This is trivial. Okay. Okay. So, right. So let me make maybe one comment about integrability and one more comment about the form of that S matrix. So what we are seeing here is that since S2 to 2 is equal to 1, right? it means that all other probabilities are 0. In particular, S 2 to 4 must be equal to 0. Right? I mean, the absolute value is 0. The S matrix is 0. And one thing that you could be a little bit puzzled is how could this be compatible with having a 3 to 3 S matrix? Right? Because 2 to 4 and 3 to 3 you would imagine should be related by crossing. I should be able to take one particle from the past and bring it to the future. Right? That's kind of what Marcos was explaining in his lectures. I start with any process. He's never discussing who is incoming and who is outgoing because he's implicitly thinking that he moves up and down wherever he wants. So how could we have 2 to 4 being equal to 0? Would it imply that 3 to 3 is 0? Because 3 to 3 cannot be 0, right? I mean, I cannot send 3 particles. Of course, I can expect to have 3 particles in the future. How could it be that 3 particles cannot just go to 3 particles in the future, right? You agree? It looks weird. And the answer to this simple puzzle is that 3 to 3 is not 0, but it's almost 0. It has one extra delta function. It has less support than usual. So the statement is that in 2 dimensions, the S matrix 3 to 3, right? It's actually equal to the following. It's equal to, the way that it works in general is like this. There is one term in the S matrix where you write it that what happens in this S matrix is that all particles are prepared to scatter 1, 2 first, then 1 with 3, and then 2 with 3. So you prepare them so that they scatter very, very, very separately. Let me be a bit more rigorous about what this picture means. I could also prepare them to scatter very, very separately, and then they would scatter in this other ordering. That is also something that should be there, because if I prepare wave packets in a different way, I could imagine that they would also scatter very separately, but in a different order. Or there could be the possibility that they would scatter in a, and now I'm not drawing the lines with the same slope, where there is another part that is what I would call the small part that is regular, a regular part that would depend on all the momenta. Okay? So this part is regular here. This part here is not regular. This part here is not regular. It will be something like this. If this is P1, P2, P3, let this guy be P4, P5, P6. And now you see, if P5 is equal to P2, then P4 and P6, they need to be equal to P1 and P3, because then the rest of momenta conservation. So let's put here one term which is something like this. 1 over, let's write a spatial part like P2 minus P5 plus some I0. And in this guy here, we will have something like 1 over P2 minus P5 minus I0. Okay? Then it turns out that this expression now, if you ask what happens if I try to convolute this with wave packets and separate a lot the wave packets and ask what happens, when you do it, you will see that what happens when I scatter wave packets that are very separated. Well, this part here, where I could just, is because it's a regular function, would not contribute if I shift. Okay, I have to be a bit, I have to explain a little bit slower. Okay, let me just say what the statement is. This part here is regular as I approach this configuration here. And this part here is exponentially small because it's regular for well-separated wave packets.
Can you just say again why you got the different I epsilon prescriptions here?
The different I epsilons works in such a way that so the different I epsilon works like this. So when you shift by a wave packet, when you have, okay, the way it works is that you want to shift the momenta up or down to move the wave packets in either direction. And your contour will be trapped. And if you prepare the wave packets, shifting them in one direction, shifting this particle all the way to the left, you are obliged, because of this I epsilon, to pick this term. Whereas if you were to shift it all the way to the other direction, you would be obliged to pick this term. Okay? Because I'm saying this out of the blue without preparing much, I will screw up if I try to write carefully, but I will prepare for next time. I will clean up this argument for next time. But now I just want to summarize to say what the result is. The claim is that all 3 to 3s matrices, they have two singular terms and a regular part. The singular terms come with different I epsilon prescription, and this I epsilon prescription is important that they come with a different one, because it's what guarantees that when I move wave packets in the right direction, I pick either this term or this term. Okay? And now you see that this term, it's a product of S matrices. You could imagine that this is a product of three functions, right? S12, S13, and S23. So if they are functions, then this product is the same as this product, right? But if they are matrices, if the particles have colors, this product is generically not the same as this product. Okay? So these two terms are different if S is a matrix, generically, right? But sometimes, so if, let's call this term A and this term B, if A equals to B, and that will happen whenever it's a function, but also when it's a matrix sometimes, and when it's a matrix, this condition is what's called the Young-Baxter equation, which is nothing if this matrix is a function. It's just product of three functions equal to product if you swap the orders. Of course, it's the same. But if they are matrices, it will be a non-trivial constraint. Whereas, and if they are true, then this S matrix, S3 to 3, is equal. Then these two guys, this minus this, produces a delta function that sets P2 equal to P1. Right? So this is like principal part plus delta function, principal part minus delta function. There is a minus sign. You get exactly a delta function. Then this S matrix is equal to one of them, it doesn't matter, times an extra delta function. Okay? So times this extra delta function that sets P2 to be equal to P5. Right? And if you remember that, let's put a hat for the full S matrix with all the delta functions, then there was another delta function for energy momenta conservation that, as we said, implies P1 equal to P6 and P3 equal to P4, right? Plus a regular part that depends on the P's times just a delta function for the total momentum conservation, right? Okay, I'm putting an extra equal sign like Marcus put two equal signs also, so I'm also putting an extra equal sign in my delta functions. Okay, I don't need it. Okay? So now this term here, you see, as an extra delta function compared to this. It's more, it is localized on a smaller measure compared to this. So what happens is the following: is if you set this guy to 0, if this guy is 0, then this is the only guy that, because it's regular, that would have support when I continue to 2 to 4. So an amplitude whose 2 to 4 is 0 is an amplitude which has no regular part. Okay? But if it has no regular parts, yeah, so then it would only be localized. Then, as you see, it will factorize, and the 3 to 3 scattering is factorized. Okay, so integrable theories are these theories where the 3 to 3 scattering is not trivial. It's not totally trivial. But it factorizes. It becomes the product of a sequence of 2 to 2 scattering. Okay? And then, because of being, although they are not 0, they are supported on this condition, that the final set of momenta is equal to the initial set. Right? So in particular, this is the key point here, is that these delta functions are implying that the final set of P is equal to the initial set. Right? And that's, of course, not a consequence of just momentum and energy conservation. In general, when you have a 3-to-3 process, that's not the case. Right? So, for example, here, that's not the case. I start with 2 momenta, and I get a set which has more particles. Right? It's not the same set. Right? It's just many more particles. Okay. So the summary is, in an integrable theory, the S matrix 3 to 3 is equal to a product of 2 to 2 S matrices. Right? And in which order, it doesn't matter. You just draw a picture and the order doesn't matter. That's the condition that the theory is integrable. Okay? So you read off, if you have particle 1 and 2, here there is an angle, theta 1, 2, and that's what would appear, say, here. Right? Then the second S matrix would be 1 and 3, and the last one would be 2 and 3. Okay. So finally, the other thing we note here is that this S matrix here has this pole, this breather. Right? And so what we see here is that in this model, I can have my particles of mass m, and they couple to this bound state. Let's call it m bound state. Okay? So let me remind you how we see in a simple way, say in quantum mechanics, for example, that the pole of the S matrix is related to the bound state. Okay? So suppose I start with my wave function for my 2 particles of mass m, that are one at position x1, one at position x2. So what would this wave function look like? There will be an incoming wave, e to the I p1 x1 plus I p2 x2, and then there would be an outgoing wave, e to the I p2 x1 plus I p1 x2, and the coefficient that maps the incoming wave and the outgoing wave is what we call the S matrix that depends on p1 and p2. Right? Now, these particles are indistinguishable, so this wave function is the same if I swap x1 and x2. Right? But we should not be fooled. So this expression is written, say, for x1 smaller than x2. If x1 is bigger than x2, you just use Bose symmetry to say the wave function is the same. Okay? Now, because x1 is smaller than x2, okay, so now the question is, so this looks like an incoming wave, and then we can ask, can P1 and P2 be complex? Could I have some complex moment? Right? Now, what happens when they are, how could they be complex? So you see that if P1 is complex, so let's say P2 is complex and it has a positive imaginary part, say. Right? Then, as x2 goes to infinity, one of these 2 exponentials will blow up. Right? So because x2 is very large and because x1 can be very negative, P1 and P2, can they be complex? Well, I have to be careful because it looks like one of the exponentials is going to blow up. So what is the way out? The way out is if the S matrix has a pole or a 0, it doesn't matter because if it has a pole, I can multiply by 1 over S, right? It's just normalization. So if the S matrix has a pole or a 0 in the right place, I can kill one of the terms. So those are the locations where I can have complex momenta, because then I kill one of the terms and I keep the decaying exponential. Right? So can they be complex? And the answer is yes, at the poles of S. And it's not just they can have poles. They need to have poles in the right place. Because if they have a pole that sends it to 0 and kills the wrong exponential, it's even worse, right? So you want to kill the right exponential. So they must have poles, and the poles must be in the right position. So when you go to the poles of the S matrix, you keep only one exponential. You write your momenta as some real part plus minus some imaginary part, the two momenta, right? The sum of the two must be real, of course. So the total momenta would be this capital P. So let's put P1, 2. Let's write it as capital P over 2 plus minus I gamma. And this gamma is fixed. This gamma is fixed by the condition that you are at the pole of S. Okay? And then what happens is that, say, this wave function would become e to the IP x of the center of mass minus gamma times delta x. So you would have a wave function that would decay away from the center of the bound state. Right? So it moves with the center of mass and then decays. Okay. And so it means that this pole here, I really can think of it as a bound state. So this guy is a bound state of these two lightest breathers. But then you see, I just gave you the S matrix between the lightest breather. But if the lightest breather can form a bound state, we could ask, can we now from this S matrix get the S matrix for, say, a light particle against this next to lightest particle? Right? Can we get this S matrix? Okay? So how could we get it? So the question is now, knowing the S matrix of the lightest particle, someone gave us this S matrix. So we have the S matrix M goes to M, right? But we also know that two M's like to form a bound state. Right? We also know that M and M, they attract each other and form this bound state. So we ask, from here, can I construct the S matrix, for example, of scattering a bound state against a light particle going into a bound state on a large particle? Can I construct now this scattering process where I have the bound state and I scatter it against a physical particle? Right? Whereas I start with this process where I have the fundamental scattering. Okay? And the answer is yes, you can do it. So, and let me explain how you do it. Okay? And the basic idea, the basic intuition, let me tell you first the intuition and then we'll go in equations and see how it works, is the following. So, in an integrable theory, you see that what happens is that the order where you scatter particles doesn't matter. And the reason is that you have higher charges that allow you to move the wave packets individually, independently. So instead of only having the usual symmetries, which are translations that only move everyone by the same amount, you can move particles differently. You can shift your particles by different amounts each particle. So then you see, here is the bound state, right? And let's scatter with this bound state here, right? So here I'm scattering with a bound state. I let these two particles here. I came back a few days after and they were in a bound state. And then I scatter, right? But I could decide to scatter much earlier before they form the bound state, right? So this, I should be able to move this particle and scatter way before they form. And then I scatter with the constituents of the bound state, right? And the constituents of the bound state, I know what they are, right? They are just the position of this. So indeed, let's see it even more explicitly. Let me do the computation that would compute this. So the first thing I want to note is that this S matrix, if I write it in terms of theta, is equal. So remember, S is cos square of theta. So it will simplify that square root very much. And the result will be just the following. Sinh of theta plus I sine of alpha over the same thing with minus sign. Okay? So that's a very, very simple S matrix. And this factor here, I will even define it because it's going to be useful in the lectures, as an F alpha of theta, and that is called the CDD factor. D is Dyson, this is Casterlitz, and I forgot the other one. Yeah, so that's that, Dyson, yeah, in particular, and it's factor. Okay, so this is a CDD factor. So that's the form of this S matrix. It's a very simple S matrix. Right? And we see that this has a pole at theta, which is theta 1 minus theta 2 equal to I alpha. Right? Good. So then let's say that theta 1 is equal to theta over 2 plus I alpha over 2. Theta 2 is equal to theta over 2 minus I alpha over 2. Right? And that's the rapidity of my constituents when I form this bound state. Right? So here is the equation. This guy at theta is equal to that S matrix at theta plus I alpha over 2 times that S matrix at theta minus I alpha over 2. Sorry, if I want the difference to be theta, yeah, minus theta. So one is going to one direction, the other is incoming. Okay? Okay. So that's the equation here. That would give me the scattering. So I'm saying that I scatter. This is like saying that I scatter with my constituents that have theta plus minus I alpha over 2. So I scatter with the constituents, and what I get is this picture here where I scatter with the bound state. Okay? Right. Okay. Let me say things a little bit more generally. How would it work in a general quantum field theory? Suppose I have a higher dimension quantum field theory and I have a 3-to-3 scattering process. Then what I can also do is take two of the particles in the past and go to what's called the Landau singularity, go to the singularity where they form the bound state. Take the two particles in the future and make their total momenta add to the on-shell value where they also form the bound state. So the 3-to-3 S matrix should have a singularity where when P1 plus P2 become a bound state and P4 plus P5 also become a bound state, the residue of this process should be the bound state scattering process. Right? But what happens is that in an integrable theory, I can write the 3-to-3 explicitly. And the 3-to-3 explicitly is just a product. Pum, pum, pum. Right? And what's the residue? The residue means that I go here and say these two guys form the bound state. So I go here and I remove it. And I just take the residue. Right? Then what do I obtain? The remaining two. Okay? That's a way of seeing how it would come about from a more general setup of Landau singularities. Okay? In fact, yeah. Okay. So this is interesting because it means that when you get an S matrix, now you can scatter, you learn automatically how to scatter the second breather with a particle M. So you see, you have a new S matrix. You can just multiply these two guys and construct a new function. What do you do with this new function? Well, you will go and see where are its poles, where are its cuts, and so on. And perhaps you will find new particles. Perhaps you'll find new poles. And then if you have new poles, okay, then you can fuse and go on. And you have to see whether things close, whether at the end you will get a consistent theory where you just don't generate a gazillion particles and so on. And that's highly non-trivial. Okay? And we are going to discuss that a little bit later. Okay. So those were the comments I wanted to make about one example of one S matrix for this theory that I called it Sine-Gordon. And I said that this guy was, as I said, the lightest breather. And this guy is the next to lightest breather. Okay. Let's do one more exercise. What do you think happens in this theory? I'll tell you that this theory has a coupling, and you can turn off the coupling and the theory becomes free. What do you expect to happen when the theory becomes free? What should happen to these expressions that we are manipulating? What should happen to the S matrix when the coupling goes to 0? What should S matrix go to? What value? 1 or 0? If the theory becomes free, what do we expect? I scatter two. What's the probability of getting two particles when I scatter two particles if the theory is free? 1. So probably 0 we can exclude. Right? Okay, so what limit would correspond to weak coupling? Well, weak coupling would correspond to alpha very small. So alpha going to 0 should correspond to weak coupling. Right? And alpha going to 0, you see, means that this is going to 1. This second term is going to 0. The second term, I remind, was the second square root. So what is happening to the mass of the bound state? It's going to 2m, and that's what makes sense, right? It's becoming weakly coupled. It's almost the mass of two particles. It's a very small binding energy because there is a very small coupling, right? So that's natural, that's okay. That just means that the mass of the bound state is going to twice the mass of the fundamental particles. It's very weakly coupled. And what is happening to our S matrix of theta? And S of theta, right? What is it when I expand? It's 1 plus 2I alpha over sinh theta. Right? Do you agree? Do you remember that we said that in 2 dimensions there's something nice, that the S matrix can be related directly to the T, to the transmission part by this expression, right? Where this sinh theta was just a Jacobian. Right? So what do we conclude that to leading order at weak coupling, what do we conclude about T of theta? Well, it's just a constant. Right? So we conclude that T of theta is just alpha or 2 alpha plus ta ta ta. Right? And what theory gives a constant amplitude? A constant 2 to 2. How do 5 to the 4. So we can already guess that this Lagrangian should be something plus alpha 5 to the 4 plus whatever. But that should probably be there, right? Just based on analyzing the kind of thing that we are getting here. Okay? And indeed, we will see that this is the case. Okay. So yes.
I can imagine a dirty possibility, right? You're bringing the bound state up to the threshold. I am an employee of the University of Colorado.
Okay.
Right? Why doesn't the scattering length diverge?
Here we are in 2 dimensions. It does matter. Scattering lengths. Why wouldn't the scattering?
I'm simply worried about having a bound. Okay, so what happens is the coupling constant is dying on you, but I'm just thinking.
Yeah.
You bring a ground state up to the threshold, and funny things happen to scattering amplitudes, right? You see the pole.
That's true, and in fact, but there's no problem with that, right? Scattering lengths are not bounded, for example.
Yeah.
So, although, yeah, okay. Okay, good. So that's it about exploration of one example of one S matrix. By the way, there's nothing wrong with just giving you the S matrix. If I give you the S matrix, and if we check that, for example, we start considering these bound states, like I said, let's do this exercise, start finding the poles, the particles, And if we find the full set of all S matrix elements, and if they define a good theory, that's it. That's the definition of my quantum field theory. So it's not like I need to give you a Lagrangian. I'm giving you because I'm generous, but I don't need to. If I'll give you an S matrix that is a consistent S matrix and obeys all the axioms, that's a definition of a quantum field theory. Okay? So this example is good indeed. It obeys unitarity. It obeys all the right properties. So that would be indeed the spirit of the bootstrap. But here we see that, okay, so by exploring this simple example, there seem to be some special theories, which are theories where the probability of producing more particles is 0. Right? So what I would like to do next is explore a little bit from a Lagrangian point of view what theories have no particle production.
Is there a way of interpreting the bound state mass going to 0? Because that would give you the same estimate. Here you go to 2m.
Right. So here you go to 2m, and you remember that I told you that you know which one is which based on the sign of the residue. So here you know that you know which one is the bound state, and the question was could I have the bound state, the T and an S channel swapped, and then instead of going to 0 to 4 it would go to 0, the mass of the bound state. So the mass of, instead of going to 2m it would go to 0. Okay? Naively, I don't expect the physics to be the same. It so turns out that because of crossing symmetry it often is. But I always like the arguments when it's about weakly coupling. I don't have a good physical intuition what happens when a bound state is becoming massless. It's harder to think. It's easier for me to think when the bound state is becoming almost at threshold. But it's mathematically, because the two are related by crossing, it's often equivalent. Okay. How much time do I have?
25 minutes.
25 minutes. Okay. So as I said last time, in the notes that I put on the wiki, there are many further problems about related to this S matrix. Writing it in various variables, checking that the residues are positive and they should be positive. For example, another exercise you can do with this S matrix is computing the 2-to-2 discontinuity that should also be positive, and you can compute the discontinuity of those square roots and check. So there are a few more exercises there in the notes that I encourage you to play a little bit if you want to be a bit more familiar with this S matrices. Okay, so next what we want to do is to consider some tree-level explorations of theories with no particle production. Okay, so the exercise we want to do is to consider a very simple Lagrangian for a free scalar of mass m with some interaction term of the form, just an arbitrary potential, phi to the n, Cn over n factorial, sum over n. And then we want to ask, are there Cn's such that my particle production of 2 going into n bigger than 2 are equal to 0 at tree level? Okay? It's a well-posed question. Start with the Lagrangian and try to see if you can tune the Lagrangian such that you cancel the processes where you would produce more particles. Okay? Okay, so in fact, to be totally rigorous, remember phi has dimension 0, so this should have dimension 2 in 2 dimensions. So we should have some mass dimension here. Okay, and it's convenient to put a minus sign as well. It's minus the potential. Okay. Okay, good. Then, what is the how should we proceed? So the idea is to first work out a few examples of small n. So the plan is first n small and get some intuition. And next is, once we see how things are working, we do general n using the multi-regi limit that we developed, because then we will be able to tame a big family of n particles, but only depending on one parameter x that is doable. Okay? So let's get some intuition at small n. So what are the graphs that would produce, for example, a t 2 to 3? Right? Well, so there are only three diagrams you can write. So if you have t 2 to 3, you can use, well, one term. Let me start with the most obvious one. Phi to the 5 produces a contact interaction. Right? That's just from the phi to the 5. If I have 1 phi to the 4 and 1 phi cube, I could also get something like this. And if I use only phi cubes, I would have something like this. Right? So these are the three diagrams that we have. Okay? So what are these diagrams more explicitly in equations? This would be C5. This would be plus C3, C4 times a summation over alpha, G of alpha. What is alpha? Alpha is, say, this subset. Is which momenta out of the 5. So alpha is a subset of the set of momenta P1 up to P5 with 2 elements. Right? And then G is the propagator of this momenta, which is of course equal to minus this one. It's the same, the propagator that flows here. Okay? What about this diagram here? Plus, well, 1, 2, 3. So C3 cube. And then I can say that this set I call alpha, this set I call beta. There's now a double sum over alpha and beta, propagator of alpha, propagator of beta. Right? So far so good. There's actually something wrong. Right? Is someone here do perturbation theory? Like this diagram is symmetric, right? So there is a 1/2 here. Okay. Very good. And now here comes a surprise. So let me put a smiley of surprise, right? It's this one. And the surprise is the following. It's something you can check explicitly. You can check that if you sum over all partitions of P1 up to P5, and here you sum also over all partitions, then the last two terms are a constant. So this is equal to C5 plus a constant if C4 is equal to 3C3 squared. Okay? So there is a value of C4, which is this special value here. And at this special value, this is a constant. The poles here precisely cancel with the poles there. Okay? Well, but if it's a constant, it's great, because then I can tune C5 to cancel that constant. Right? If it was not a constant, forget about it. I cannot cancel with C5. Right? If it had some non-trivial dependence, I cannot cancel some non-trivial function of momenta with a constant. Right? Okay, so that means that all we need to do is pick C5 to be equal to what? Well, I would have to tell you what that constant is. But do I know what actually the constant is? I don't know. But we can cancel. Do I write here? I don't. Okay. So we can pick C5 equal to minus that constant. Right? So this is a nice identity. You can check. You can take the residue at one of the poles and check that there are some nice identities of sum of poles that cancel. It's a little bit non-trivial, but you can easily do it. I mean, you can put it in Mathematica and check.
For the last diagram, I used to put C3.
Yes, of course. C3 cube. Right? 1, 2, 3. Great. Good point. Right? That's why C4 wants to be C3 squared, so that the total power is C3 cubed, right? And then this C5 will be proportional to C3 cubed. Right? Well, then we go on, right? So now we go on, at least one more term, we will still do it. So let's write what would be T 2 to 4. Well, let me write it down. Let me write with this diagram is symmetric, so there will be a 1/2 times every 1 cubic. 1, 2, 3, 4, 5, 6. Plus this diagram, plus 1/2, plus 1/2, plus 1, 2, 3, 4, 5, 6. Yeah, it's good. No. Plus 1/6 plus contact interaction. Right? Where you can translate everyone. And now, again, another amazing surprise is that now all these terms here we fixed already, right? All these terms here are fixed. You see cubic terms and so on, quintic terms that are fixed already. Now there's nothing to fix. All couplings here are fixed. And now you have to hope that it works, and indeed, it beautifully works, that all these terms are a constant.
So that's assuming the same relation that you got.
Right, now we assume that. Now we fix these two relations, and we check that these guys are a constant. Okay? And then it means that this constant, I'm going to set it to be minus C6. Or I would set C6 to be minus this constant. Right? So at this point, we could code in Mathematica, and we did a few more terms, and try to guess a pattern. You can compute now C3, C4, C3 is free. You can compute C4, C5, C6, C7, and try to see if there is some pattern. Okay? So I can show you, for example, how the potential would look like. 5, 6, one more term. This and one more term. So far, this is where we are. But as you will see, it's not so obvious to guess. So we will have to be smarter, but that's what we are going to do next. But at this point, just based on a few examples, to try, as I said, to try to get some intuition, here is what we would get. So right now, we are getting that our L interaction is equal to minus m squared, and then we are getting C3 over 3 factorial phi cubed. Then C4 was 3 C3 squared over 4 factorial phi to the 4. Then C5 is this constant. The constant turns out to be minus 5. So what you need to put here is 5 C3 cubed divided by 5 factorial phi to the 5. Right? Okay, so far so good. And then you can compute what that constant is, that C6. That constant turns out to be minus 11. So you want to put here plus 11 C3 to the 4 over 6 factorial phi 5. And you can go on. The next constant turns out to be minus 21. So you put plus 21 over 7 factorial phi to the 7 plus Okay, C3 5 plus Okay. So that's it. That's the Lagrangian that you are getting. That it's not so obvious what it is, right? We are getting 3, 5, 11, 21. It's not the most. They are not the most obvious numbers.
Last term on the top should be 5, 6.
Sorry?
The
5.
The last term on the top should be 5 to the 6.
Yes. Good. Okay. So now the idea is assume we can proceed, right? Based on this intuition, it seems obvious. I mean, doesn't seem any sign that it fails. So assume we can proceed, but then if we believe that we can do it, let's do it using the multi-Reggie limit. Let's impose that you have no particle production in the multi-Reggie limit. Now, what happens in the multi-Reggie limit? So this limit here, right? I remind you what happens. Remember what I told you, that the propagator, now at 3 level, always separates the left and the right part. We go to any of these propagators, right? And when I consider this propagator, any propagator separates the left part and the right part, right? And then we said that in this multi-Reggie kinematics we have something remarkable, that the propagator of alpha on the left, which is of course the same as the propagator of alpha on the right, that this was equal to 0 unless alpha, one of them, was equal to a sequence 1, 2, 3 up to j. Unless alpha is an ordered sequence, we got 0. That was because if it's not like this, if one of the sides is not the ordered sequence from 1 to j, you are exchanging too much energy and the propagator dies off. So we needed to have this hierarchy of energies. So the particle that is quiet wants to be on the same side of the particle that's almost quiet and exchange just a little bit of momenta. If on the left we have a lot of momenta, that kills the propagator, of course. Right? So it's equal to 0 unless this happens. But what was even more than this, it was equal to -1 otherwise. Right? When we are here, when alpha takes this set, the propagator was just -1. Right? Now, this is a huge simplification. Because let's look, for example, here. Right? Let's look at this graph here. Right? Or, yeah, let's look at this graph here. So you see that here, what do I have? I need to put the particles 1, 2, 3, 4, 5, 6. Instead of summing over all permutations, they need to be ordered. Right? Well, there is this and there is the opposite order, which is the same. So it just cancels the 1/2. It cancels the 1/2, and what does this propagator give? -1, -1, -1. So all this graph, all this huge sum of permutations, blah, 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 becomes just -1 cube, 1, 2, 3, 4, C3 to the power 4. That's it. I took care of this term. Right? And now we can go on like this. So this one also -1, -1. So this diagram is just +1 times C3, C3, C4. C3 square, C4. Right? And yeah. And I can start 1 here or 1 here, so there is a factor of 2 from the two orderings. Right? What about this graph here? Remember, this was the one I said at the end of the last lecture. What happens? Can I always separate a set from the other? Let's see. Imagine I separate here. Okay, fine. I can put 1 and 2 here. Right? Then suppose I separate here. Okay, then now I need to put n-1 n here. But now I'm destroyed, right? Here it doesn't work. This side doesn't contain a sequence starting from 1. So this diagram, for example, is equal to 0. Right? So I only keep diagrams that have the structure of a line, and furthermore they need to be all ordered, and each of them just gives 1 or -1. Right? So now you can really compute this constant straight away and find the -7 that we got there. Okay? But what is more, now we can write a recursion relation very easily, knowing this. Okay? So let's assume that n particles was cancelled and impose that n+1 is cancelled. Right? So we want to impose that 0 is equal to t 2 to n. Okay? That is equal to what? Well, one term is the maximum term, C 2 plus n. Right? Then there is, so let's look at where 1 attaches, where the first particle attaches. It can attach to the maximum vertex, then the diagram is done. Or it can attach plus to the one that has almost the maximum. You see, one leg is missing, and then here there is a cubic coupling. Right? So this would be Cn plus 1 times C3. Right? Or the one could attach to or what it could do is, yeah, that's correct. Or it can attach okay. Oof. Or it can attach to one where I have 2 less particles here. And now here I have 2 options. I have the 2 cubic guys or a quartic guy. And this graph would be Cn plus 1. This would be Cn, C3 square. And this would be Cn times C4. Okay. And then the claim is that it stops here. Now plus 0. Right? Why 0? Because the ones that have more structure on this side, we already showed that they add up to 0. Okay? So again, that's, let me, yeah. So this is the induction step. So you can show that if you add more structure here, you already showed that it cancelled. And so you end up with a relation. Let's do it carefully now in the multi-Reggie limit. This propagator here was minus 1, so there is a minus sign. These propagators are 2 minus 1, so plus. And here there is one propagator, minus. And so we end up with this recursion relation, that 0 is equal to Cn plus 2 plus this plus this. This term, remember, was fixed, was 3 times C3 square. Right? And now you get immediately a recursion relation for Cn. Right? And immediately you find the solution, which is that Cn, the numbers we were after, it's 2 plus minus 2 to the n divided by 6 times, let me parameterize it with lambda to the n minus 2. Where in particular, when you put n equals to 3, lambda is C3. Okay? And then, if you take this C, you can now go and ask what theory corresponds to this C, right? You have the interaction Lagrangian. And that gives you a Lagrangian, which is d phi square over 2 minus m square over 6 lambda square 2 e to the lambda phi plus e to the minus 2 lambda phi minus 3. Okay? So this is a Lagrangian that is, you see, if you expand that small phi, this thing becomes phi squared over 2, that's the mass term, plus phi to the 4, plus phi cubed, phi to the 4, and so on. And this is called the Bullock-Dugg Lagrangian. It's, okay, this stands for Bullock-Dugg. And as you see, it's the theory with a single scalar and a cubic interaction. So this theory, there exists a cubic coupling, right? And has no particle production.
Is there any minus 4 to the n in the denominator for Cn? Because if you plug in some numbers, it could be some negative numbers, but the
2 plus minus 2 to the n. The question is, these c's, they look like they are becoming negative when...
But if you put some minus 1 to that,
let me first check that the signs are correct. Let's see. Yeah, okay, it's a good exercise. You can... Yeah, those c's look correct to me. So I suspect there are minus signs missing in the expression I wrote there. Yeah, so this expression is this is correct. Okay. Now, this theory actually is not the Sine-Gordon theory. This is Bollock-Dugg, is one which is much less known than Sine-Gordon. And Sine-Gordon, to go to Sine-Gordon, we would have to go back a few steps, because Sine-Gordon is a theory that has Z2 symmetry. So we have to change a few steps in our calculation. So here, the first thing we started doing was canceling the 2 to 3 process. Where is it? Here. But we could ask what happens in a theory with Z2 symmetry. Right? So a theory with Z2 symmetry, let me do it in a different color. So let's do it here with a different color. Let's say with Z2. Okay? So what happens when I have Z2 symmetry? Here I sum over n even. Right? There's no c cube. There is c4. There's no c cube. So this is just 0, right? 0, 0, 0. So there's no 2 to 3, of course. Right? There's no cubic. There's no amplitude. So our game would start canceling this guy. Our first game would be canceling the one that before was the second guy here. Right? So that's where we would start, is canceling t to 4. And which terms would we cancel? So there is no such term here, because this has cubic interactions. This has cubic interactions. This has cubic interactions. This has cubic interactions. 1, 2, 3, 4, 5. This has cubic interactions. So the only term that survives is this, when I have Z2 symmetry, and the contact term. Right? So the analog of this first miracle here, which is that these two terms add up to a constant, now is the question, is the sum over partitions here, alpha and beta, a constant? If so, I can start the game and then use the technology we did before. And indeed, this is just a constant. Okay? And because this is a constant, I can cancel it with C6. Okay? So good. Then the rest of the logic follows. And that's why in the recursion relation, I did not plug C4 right away, because I wanted to keep the recursion relation with C4. Because now I can go to the recursion and put C3 to 0. Right? In this recursion, this term is not there, this term is not there, and only this term is there. So what do we see from this recursion relation? That Cn is equal to Cn plus 2, plus some constant. Right? Do you agree? And so we get that Cn is just some lambda to the n. Right? And what do I get when I sum lambda to the n over n factorial over the n even? I get cosine. Okay? So indeed, the potential that we end up with a Z2 symmetry is m square, let me use a different notation, over beta square cosine of beta phi minus 1. Okay? And that is the Lagrangian of the Sine-Gordon theory. Okay? Now this Sine-Gordon theory, it's an interesting theory, right, where I have this potential, this periodic potential, right? And the breathers are the fundamental excitation of this phi. I can think of phi, and I think of a small wiggle, and that's a breather. And these are not the only excitations in this theory. For example, you can think that phi equals 0 or phi equal to 2 pi over beta is the same thing. So you can, in this theory, you can also have another type of excitation, which is that you start with phi and you move to a different vacua. Like you go from 0 to 2 pi over beta. And then this domain wall is called another type of excitation, which is a kink. Okay? Now, what you can also do is produce a king and then an anti-king. Now you are back to having trivial, back to the same vacuum. And what happens is that this king and anti-king themselves attract and form a bound state. And this bound state is the breather. It's another way of thinking of the breather. Okay? So in the end, Sine-Gordon has all these breathers.
Pedro?
I'm finishing.
Okay, about 4 minutes over.
Okay. We have all these breathers. We have kings and anti-kings. And they are all related at the end by fusion. Okay. And so next time I will start by summarizing a little bit what we did, and in particular by commenting that this was an exercise we did at 3 level, and we found 2 special theories, right? And we can write their quantum S matrix. I started the lecture by writing what the S matrix for the lowest breather of this guy is, and I will start tomorrow by writing what the S matrix for this single scalar is for this theory. And then we could ask what would be the quantum version of this no particle production. And in fact, it will nicely close to what I said, that these fusion relations that we wrote today are what guarantee that there is no particle production at the quantum level. So these fusion relations, that S times S is equal to S of the bound state, is actually equivalent, reduces at 3 level to the exercise we did, and guarantees no particle production at the quantum level. And then we will go, so that's what we are going to do in the beginning of next lecture, and then we'll start going into the Bootstrap now that we have some experience with 2 to 2 and 2 to n particles. Okay, I'm good, thanks.
How successful is this game at exploring the space of integrable theories? In terms of like finding new ones or...
Yeah, so all these games of writing this recursion relation and so on was something we did with Barak and others, and we found some recursion relations that reproduce known integrable theories, allow us to find some families of Toda theories that were known before. We don't know if the solutions of the recursion relations have more solutions. These ones, with a single scalar, it's done. We solved it, right? We finished. But when you have more than one scalar, the equations are matrix recursion relations that we don't know if we explore the full space of solutions. Yeah, but yeah, I think it's it's a very efficient way of finding these 3-level Lagrangians. Yeah.
Can one make sense of any of this story in the massless case? Zamolodchikov has these massless S matrices.
Yeah, in the very last lecture, I'm going to discuss a little bit massless scattering. So when you scatter massless particles, there are 2 very opposite extreme regimes you can consider. One is where a left mover, a particle moving at the speed of light to the left, and the right mover, one moving to the right, they scatter non-trivially, but left-left and right-right scatter trivially. The other extreme scenario is the opposite. It's just left-left scatters with left-left, and left and right don't scatter, right? And depending on the situation, you can have either of them. So, and I'm going to discuss a little bit the case where you only have left-right scattering. Zamolodchikov sometimes discuss the case where you only have left-left scattering. And conceptually, that one is harder to understand, right? Because if you have 2 particles moving at the speed of light, how are they going to scatter if they are moving in the same direction?
I have a question. When we did the Bullock-Dug case, we started with the 2 to 3 and showed this condition.
Yeah.
This should tell us something about 2 to 2 scattering also, right? We learned something about 2 to 2 scattering from that condition?
Yeah, that's true. So eventually, that's true. We learn that 2 to 2 scattering, that there is a contact interaction and there is an exchange, and the coefficient of the 2 is finely tuned.
Nice interpretation of that, or is it just a relation?
So I will show that the 2 to 2 S matrix of Bullock-Dug, because the Bullock-Dug has a cubic particle, the bound state is the particle itself. So Bullock-Dug has the property that, which is true in any theory that you get a pole in the S matrix of the particle itself, you can say the particle is a bound state of itself. So Bullock-Dug, you take 2 particles, you fuse, and you get back the same particle. So it obeys an equation like I wrote for the S matrix, where you get S times S equal to S itself, and not to a new S. And that kind of consistency equation would be the quantum version of this consequence that you are pointing out here. But then I will explain why that relation also guarantees no particle production. But that will be tomorrow.
Just to close that issue, C3 is just related to C3 squared
Ah,
is related to
yeah, yeah, yeah.
squared with a minus
Yeah,
sign.
yeah, yeah, yeah.
That solves that.
Yeah, something like that. Yeah.